So to come back, theta is an unknown parameter, non-random, and we have data. And theta hat is an estimate for theta based on the data, obviously. So this is an unbiased estimator. So among all the unbiased estimators, how do you find the one with the minimum most variance? So interestingly, what we are going to see is the sufficient statistic for the data will play a role here. So we have this going on. Anytime the data is given and you know the joint PDF of the data, then we can come out with the sufficient statistics. Remember, the sufficient statistics is such that the joint density function can be written as a product form, right? So one part involving the parameter that we are interested in and a function of data, and then this is the sufficient statistics. That's the factorization theorem. And the other part is just junk. Obviously, it's not a function of theta, but it has to depend on something which will be data, right? So to make it short, the answer to this question is given by this theorem. So estimator with so theorem says that the estimator with the minimum variance is unique and given by so an unbiased estimator for theta with the least variance is unique and is given by expected value of hx given t. Where hx is any unbiased estimator for theta. Or so to put simply, if hx is such that if hx is an unbiased estimator, in other words, expected value of hx is theta, then the theorem says expected value of hx given tx So I hope it is clear, at least the statement, right? So what it says is one way or the other way you find an unbiased estimator for theta. Then the conditional expectation of that unbiased estimator given the sufficient statistic. Remember, as in probability, a conditional function, the conditional value of x given y will be a function of y. So whatever you are conditioning on, it will be the whole quantity will be a function of that. So this will be a function of t only. T is the sufficient statistics. Yes, that is clear, right? So what the theorem says is that this conditional expectation is the best estimator for theta. And that's the Rao-Blackwell theorem. So let me prove it, then we'll go through several examples, then I'll give you some of them are reasonably easy, some of them are little more harder. Then I'll give you a few problems to solve at home and etc. Right. Any questions on this statement? So the problem is completely solved from this theorem. The best estimator is given by the, so you can say I think a couple of weeks back, you or someone asked me what is the meaning of, what is the significance of sufficient statistics. You can see it here. Sufficient statistics has the unbiased estimator information in it, which function of course depends on theta. So sufficient statistics is, as the name says, it has everything in it, including a functional form which is unbiased for theta and with the minimum most experience. Alright, so let me prove this, then I'll go into several examples. So let me ask you this, if you find an unbiased estimator which is already a function of sufficient statistics, what can you conclude? Huh? So if you, one way or the other way, if you find an estimator which is already a function of sufficient statistics, you are done. There is no better estimator. I mean, if it is unbiased, I meant, right? That has the minimum most variance from the problem. So this is more practical than the Cramér-Rao bound. Yes and no, but in complicated problems, it may be very hard to find the actual form. So of course, Cramér-Rao bound doesn't tell you how to find an estimator. It gives you a lower bound. This is telling you how to find a lower. And I'll show you some problems which are easy and some which are not that easy. So let me, the proof is from Professor Rao's book. Let me call T0 to be that unbiased estimator, right? So of course, you know, T0 will be only a function of T, right? Is this clear? Yeah, that's very clear, right? So let's look at expected value of T0. So that's going to be expected value of hx a given t. So anybody, what will be this? Expected value of x given y is what? Expected value of what? Not tx, hx, right? So that will be hx. But look here, hx is already unbiased. So the first thing we proved is that this is unbiased. Okay, now so let me show, before I proceed with that, let me show that they have, it is unique. So if T1 and T2 both have minimum variance, then I am going to show that, I want to show that T1 is T2. In other words, both are unbiased. And both their variance is the minimum, okay? Then this is what I am going to show. I am going to show that T1, the estimator with the minimum variance is unique first. So first let me show the uniqueness part. Take T to be T1 plus T2 by 2. Then what is the mean of T? Anybody? That's mean of T, as you can see, is theta. So that's unbiased. And let's compute the variance. So the variance of T is expected value of T1 plus T2 by 2 minus theta, the whole squared, right? So if you expand this, take this 2 here. So that will be then T1 minus theta, T2 minus theta. So you will get the first expression will be variance of T1 plus variance of T2, right? Then minus 2 times expected value of T1 minus theta multiplied by T2 minus theta. That's covariance of T1 comma T2, right? Yes? So look here, let me call this minimum most variance to be sigma min squared. Remember what I'm trying to show. I'm trying to show that the estimator with the minimum most variance is unique. So if not, let's assume that there are two estimators with the minimum most variance. Then this estimator, which is unbiased, has to be, its variance cannot be greater than this, right? So it has to be greater than or equal to, it cannot be less than this, right? Because this is the minimum value. So T has to have variance which is greater than or equal to the minimum value, okay. But remember, this is sigma min squared, this is sigma min squared. So you take this 4 here, this gives us the expression that covariance of T1 comma T2, you can see here, this is plus here, right? Because you know how this I wrote it as T1 minus theta plus T2 minus theta divided by 2. So this will be 2. So this is 2 sigma squared. This 4 comes over here. So you can see this will 2 sigma squared will go away. Then 2 will go away. So this gives you that this expression, right? But on the other hand, you have this expression, right? Covariance of T1 comma T2 is less than or equal to sigma 1 sigma 2, right? Covariance, right? Because covariance divided by sigma T1 sigma T2 is a rho, correlation coefficient, which is, this expression is from standard for 2 random variables. So this means that this is also less than or equal to sig mean squared. That means the covariance is 1. That's what it means. That means T1, probability of T1 and T2 are coherent, or T1 equal to is essentially 1. Probability T1 equal to alpha T2 almost everywhere. But then expected value of T1 equal to, look at here, expected value of T1 and T2 are theta. So expected value of T1 equal to expected value of T2 equal to expected value of alpha T2, because alpha T2 is T1. All this is equal to theta. So you get alpha equal to 1. This means that T1 equal to T2 almost everywhere. Because look at here, T1 equal to alpha T2. So you pull out alpha, but expected value of T2 is also theta. So alpha must be 1. So you get T1 equal to T2. So what is the, so first we have shown that the estimator with the minimum most variance is unique. And the rest of the proof is easy, so I'll just complete it. Okay, any questions on the uniqueness? You?
Sigma means square, right? Covariance given.
What?
Covariance given, or is that correlation given equals 1?
No, what is the expression for, remember? Correlation coefficient is covariance, sigma x, sigma y, right? Here sigma x and sigma y are equal. Sigma min, okay? So, but correlation, as you know, this quantity is less than or equal to 1 in absolute values. Yes? And so that is how you get this. Because that means this is less than or equal to 1. So covariance is less than or equal to sigma squared. Is that the question? Or?
Then the next line is
Here? Yeah, but look at here. Here it is the other way. So you have to, together with these two. First we proved that covariance is greater than sigma squared. Here, but covariance has to be less than or equal to sigma squared. So this together with this will give you this. Because equal sign is the only option, isn't it? Yes? Yeah, so first we wanted to prove this, and then we have this freebie. So this together with this gives you this. Oh yeah, if that's what you're asking. Yeah, yeah. What I meant was correlation equal to 1. Is this what you're saying? Okay. This means T1 and T2 has to be the only option. This means correlation is 1, right? If correlation is 1, T1 and T2 are coherent. T1 and T2 are coherent means T1 is a constant multiple of T2, T1. And that constant we are showing has to be alpha. I mean, has to be 1. Yes? Thank you. I mean, I meant 1. No, I didn't mean 1. I meant the sigma squared. Right? Okay? Any questions? Yeah, yeah, right. Thank you. So the remaining proof is, this is from Professor Rao's book. So I guess we showed the uniqueness. Now I am going to show that all I need to show is that this T naught, you take any arbitrary, so let me start with Hx is any unbiased estimator for H. I'm going to start with this. Hx is any unbiased estimator for theta. Then I'm going to do the conditional expectation of that Hx given T, given the sufficient statistics. And let me call that to be T naught. And I just showed you that T naught is an unbiased estimator for theta. Now I'm going to show that, well, what we want to show is that the variance of T naught is going to be less than or equal to variance of this estimate, variance of Hx. This is what I want to show, okay? But what is the definition for the variance? Anybody? Variance of x is what? Expected value of? Or x squared minus the mean squared, right? So this is going to be expected value of T naught squared minus, what is the mean? All right, so minus theta squared. So we want to show, look at here. Here it is going to be expected value of Hx squared minus theta squared, right? So theta squared is common. So what we want to show is expected value, we want to show that expected value of T naught squared, which is, I'm just going to substitute for T naught. T naught is expected value of, where is it? H of x given T of x. So we want to show that this quantity, I'll keep putting a question mark because we want to show whether this is true, is less than this. So this I can write this as yes? Look at here, any random variable, expected value of x squared, of course I can write it as expected value of x squared given like this, right? Expected value of x squared is the same as expected value of x squared given y. If you know how to read it, that means the inside expectation is with respect to x, outside is with respect to y. So this is true. So instead of writing a expected value of h squared, I wrote it as squared given tx. Okay. So if you can show that this side is less than or equal to this side, so now you see so with this expectation being on t, this expectation is of course being on t. If we can show that this quantity is less than or equal to this quantity, then we are done. So let me just copy that here. So we need to show expected value of hx given tx, the whole squared, is less than or equal to expected value of h squared x given tx. This is what we want to show. If we can show this is true, then the T naught has the minimum variance, and it is already unique. We have shown that. Okay. Now this is true for any random variable. So let me just show you this somewhere here. So let me expand this quantity. This quantity is what? Expected value of x yes? Expected value of x given y, the square is outside. So that's, I just, expected value is integral x, the conditional density function of x given y dx. So this I'm going to write this as in the next step. Anybody? Now what do I do? Look at this is an inner product of two functions, ax, bx squared. So what do we do? Cauchy-Schwarz, right? So this is less than or equal to, remember, a squared multiplied by b squared, right? Dx, etc. So let me substitute for a squared is, look at here, integral x squared fx given y, x given y. And b squared is integral fx given. What is the integral on the second integral? Anybody? This is a conditional density function of one random variable. So what's the area under a random variable? A under a density function. So this is 1, right? And this is expected value of x squared given y. So we proved this. This is all true for any random variable. Expected value of x given y, the whole squared, is less than or equal to expected value. And that's what we have, look at here, that's what we wanted to prove here. If you read expected value of x given y, the whole squared, is less than or equal to expected value of x squared given y. And there's a little more to it. I'm not going to, the proof is here. And the question is, when will you have equality, right? So equality will have when you can show that when hx is essentially a function of t, hx is a function of t itself. In other words, if that you can see easily. If h happens to be a function of t, then this whole thing will be, on both the sides, it will be exactly the same thing, right? And then that's the only case. You still need to go through a couple of lines. So if hx is a function of t, then you have equality. So with this, so this is Rao-Blackwell theorem. So let me do a few examples to show you how to solve a certain, so the theorem will be useful in certain cases. So if we are done, so remember, then earlier we showed uniqueness. And so from here, wherever the uniqueness part, I should have mentioned that from that probability expression, to get the T1 equal to T2, you need completeness for the whole density function. So in that case, this would be, so this procedure is called Rao-Blackwell procedure. So what is the procedure? Look at the moral of the story. You can start with a sloppy estimator. Then to get the best estimator, you just have to find the conditional expectation of that sloppy estimator conditioned on the sufficient statistics. So the sufficient statistics will do the job of cleaning it up and pushing it to the right spot with the minimum most. So in problems where you can solve this, you do this, right? You find a sloppy, remember we always do this, right? When you want to make a knot, you put a knot, then you tighten it to wherever position you want. This is exactly the same flavor. You come up with something sloppy, at least you get into the bus, then you look for a good seat and then sit, something of that sort here, right? So if you can find a sloppy estimator, you can make it better by going through this procedure, right? So this is the moral of the story. So Rao-Blackwell theorem says start with any unbiased estimator hx for theta. Then you can make it better. Then if you do this conditional expectation of that hx given the sufficient statistic, this will be a function of t. This is the best estimator. So this is of course unbiased estimator and it has minimum most variance. With the minimum variance. So if you, as a couple of examples, let's say, remember theta equal to mu, we already know. So let's look at. So let's say the data is normal with mean mu and variance sigma squared. So you have independent identically n samples from a Gaussian distribution with mean mu and variance sigma squared. So we went through this. So if you think mu is your, first of all, the sufficient statistics here is sigma xi, right, or sample mean. You can divide by a constant, that doesn't change anything. So this is the sufficient statistics for mu. We did this earlier. And we also know that this happens to be normal with the mean mu and variance sigma squared over n. So we did the Kramer-Rao mount for log f is what? Log of 2 pi sigma squared to the power n, right? Minus n log n minus so if you do log of f with respect to mu, you get what? Sigma xi minus mu over sigma squared. So you do it one more time. So you get minus n over sigma squared. So from here the Kramer-Rao bound for mu turns out to be sigma squared over n. And the first thing here is, look at here. this is unknown, but we found this is a sufficient statistics which itself happens to have mean mu. So this is an unbiased estimator for mu. But this unbiased estimator is already in terms of sufficient statistics. So we know that this is the best estimator. Here, of course, if you compute its variance agrees with the Cramér-Rao bound, so this is also efficient estimator. But if you take, suppose you say the mu squared is your unknown, then first of all, we can quickly compute the Cramér-Rao bound for mu squared. So from what I said earlier, that's the Cramér-Rao bound for mu multiplied by d mu squared over d mu the whole squared, right? Phi is mu squared, so that's going to be 4 mu squared sigma squared over n. That's usually the easy part. Now the question is, we want an hx, right? But remember, this is a problem we have done. So I think it was this, right? This is an unbiased estimator for mu squared. This is unbiased because, look here, expected value of hx is, where is it? Look here, expected, x bar is with mean mu and variance sigma squared. So the square of the value is mu squared, mean squared plus variance, right? Or minus sigma squared over n. So that's mu squared. So this estimator, here of course I am assuming sigma squared to be known. So look here, this is already a function of sufficient statistics. So I don't have to go any further. We know that this is the best estimator for this problem. That's the value of the theorem now. Now, if you want, you can compute the variance of this estimator. What was it? Can you read it? So that turns out to be 4 mu squared sigma squared over n plus. What was it? What was the term here? 3 or 2? We just did it a few minutes earlier. So clearly you can see this estimator is not efficient. But this is the best one because it's a function of sufficient statistics. So let me do a little more complicated examples. And then I'll come back to the big problem of estimating both mu and sigma squared and sigma. So, but let me warm up with one more problem.
Two unbiased estimators, H1 and H2, and you take the conditional expectation of both H1 and H2 given Tx, will they be the same?
Yeah, that was remember that was the whole point of earlier, uniqueness. Uniqueness says you can start anywhere, all the roads will lead to the same place. So obviously do the one with the least work. So look at this Poisson problem. So I'll do 3 examples here. Xi's are Poisson, I equal to 1 through n, and IID, independent identically distributed Poisson. So the joint density function of x1, etc., xn is what? E raised to minus n lambda, lambda to the power x1, x2, etc. Remember the product, so sigma xi over xi factorial. So anybody from here, what is the, using factorization theorem, what is the sufficient statistics? Anybody sees anything? Because this is your hx, this is your g, right? So this is where the data comes in, right? So t equal to sigma xi is a sufficient statistics here. And that's Poisson with the parameter n lambda, right? Because sum of independent Poissons are Poisson. So this is where the probability helps you. So let's do 2-3 problems. I'll do this one at a time. So 3 different problems. First we are interested in the best unbiased estimator for lambda, then for lambda squared, so the first 2 are reasonably easy. That one that one where we really need to use the theorem. So we can use common sense. Look here, the answer is screaming in front of us. Expected value of this is what? Anybody? Huh? N lambda. So how will you get an unbiased for? All right. So that's easy enough, right? So x bar, which is 1 over nt, is how mu? Is because that's also a function of sufficient statistics. So that's the best estimator. I mean, but I think we did this, but I'll quickly do this. So its expected value is lambda. And what is its variance? What is the variance of t? Anybody? What is the variance of Poisson random variable? Not lambda squared. Poisson, the parameter is the mean and variance, right? So variance is also n lambda, okay? So variance of t is n lambda. So what is the variance of x bar, this unbiased estimate? So variance of x bar is 1 over n squared variance of t. You see that it's a constant, comes out as square. So that's going to be lambda over n, okay? And if you want to find out the little more about this density function, so this is already the best estimator, right? Just curiosity's sake, let's also find the Cramér-Rao bound in all these cases. So that's going to be log f is minus n lambda plus sigma xi log lambda, right? Minus log of product of xi. So I'm going to take the derivative of the logarithm of the density function with respect to lambda. So that's minus n plus sigma xi over lambda. So I'm going to take the second derivative. So that's going to be minus sigma xi over lambda squared. So let me take the expected value of that. So expected value of d squared log f over d lambda squared with a minus sign is lambda. So expected value of this is expected value here by, so what is the expected value on the numerator? Anybody? N lambda. Lambda will cancel, so you will get this to be n over lambda. So you get, from here you get the Cramér-Rao bound for lambda is minus 1 over expected value of d squared log f over d lambda squared. So that will turn out to be lambda over n. Look here, the variance and the Cramér-Rao bound agrees. So this just happens to be also an unbiased, efficient estimator, right? So let's look at the second one. So let's say theta is lambda squared. So remember, to use Rao-Blackwell theorem, all you need is an unbiased estimator for lambda squared, right? So let's look at, if x is Poisson, anybody, expected value of x is what? Anyone? Lambda. Expected value of x squared? Huh? What is the variance? So what is the, if Expected value of x squared is square of the mean plus variance. So that's lambda plus lambda squared. We will need this, so I'm just going to ask you, what's the expected value of x cubed? Do you know how to compute it? An easy way? For Poisson, this formula is true. Have you seen this formula? Or?
Yeah.
So for Poisson, expected value of xk is lambda multiplied by expected value. You seen it? Everybody? Or, of course, or some of you are seeing it here. Well, you see, this is easy to prove. So this is summation, what is it, x to the power, let's say xn. So this is k to the power n, e raised to minus n lambda, lambda to the power n over n factorial. Lambda to the power k, right? K is the variable. K goes from 0 to infinity. Now look at the argument. You have to be careful here. Because K is here, when you substitute K equal to 0, what happens? The whole thing vanishes. So you can put this 1 through infinity. That's the same. Now it is all non-zero, so I can cancel 1K here. So this will become n minus 1. So this will become k minus 1 factorial. So what is it? And so I have k minus 1 here, and I have k here, so I'm going to make this k minus 1, and I'm going to pull a lambda outside. So I'm going to put, let's see what the terms come up with. And so this is going to be summation now, k to the power n minus 1, e raised to minus lambda, lambda to the power k minus 1 over k minus 1 factorial. But k, remember, goes from 1 to infinity. K going from 1 is the same as k minus 1 going from 0 through infinity. So I can rewrite this using a new variable, m 0 through infinity. Instead of k, I'm going to, instead of m is k minus 1. So k is m plus 1. So this will be m plus 1 to the power n minus 1, e raised to minus lambda, lambda to the power m over m factorial. So this is expected value of, see this one, x plus 1 to the power n minus 1. But there is a lambda here, right? So this is this formula, which is what I have used. So because I need this, let me just compute this when I am here, or we can compute it later. So look here, so this will give us a clue here. Expected value, so this of course if you want you can write it as, so this will give us a clue for an unbiased estimator for lambda squared. What is it, anyone? Expected value of x squared is from here. Subtract what? Lambda squared is what we want. We are looking for an unbiased estimator. So let's see what's this one. So let's see what's the expected value of t naught. So that's expected value of t squared minus t, expected value of t. So t squared is what? T is somewhere here. T is Poisson with parameter n lambda. So this is n lambda squared plus n lambda minus n lambda, right? So this cancels. So you can see if I divide this by n squared, then everything is good, right? So this is the best estimator. Why? From the theorem, we found an estimator which is a function of sufficient statistics. If you want, the question is what is the variance of this? So let me call, remember, so this is what I'm calling T naught. T naught is this over T squared. We know that the expected value of T naught is lambda squared. And what is the variance? So variance of T naught is 1 over n4 square of this expected value of T squared minus T the whole squared, or minus lambda 4, right? Minus the mean squared. So you have to compute this quantity. So that quantity will turn out to be 1 over n4 expected value of T4 minus 2T cubed plus T squared, right? Minus lambda 4. So this is where we need this. So let me just complete these two so that we can complete this problem. So this is, this when you expand, what do you get? Expected x squared plus 2x plus 1. Expected value of x squared is already here. So this is expected value of x squared plus 2 expected value of x plus 1. So that's going to be lambda multiplied by lambda squared plus lambda plus 2 lambda plus 1. So that's going to be lambda cubed plus 3 lambda squared plus lambda, right? So let's do this. So this is going to be expected value of x3 plus 3x squared plus 3x plus 1, right? So that's lambda multiplied by x cubed is here. So you can do this by chain. 3 lambda squared plus lambda plus 3 times x squared. X squared is lambda plus lambda squared plus 3 lambda plus 1. So that's going to be lambda 4 plus how many lambda squared? See here, lambda squared here, 3 lambda squared. So 6 lambda cubed plus 3 lambda, 1 lambda, 7 lambda squared plus lambda, I guess. Is it? So now you substitute, because T is, look here, T is Poisson with parameter n lambda. So if I put it here, I don't need this. I do need this value. So if I put this here, so this is going to be 1 over n4. So expected value of T4, which is here. Remember, T is parameter, not lambda, n lambda. So this is n4 lambda 4 plus 6 n cubed lambda cubed plus 7 n squared lambda squared plus n lambda. So I just took care of this term. Then minus 2 t cubed. T cubed is here. So minus 2 n cubed lambda cubed minus 6, because this 2 multiplied by 3, minus 6 n squared lambda squared minus 2 n lambda. So we are up to here. Then this t squared is lambda plus lambda squared. So that's n squared lambda squared plus n lambda. Now I don't need this, so I'm going to remove this. So N4 cancels. So this is only this term, minus lambda 4. So I hope you are able to see. So this N4 cancels with the N4, you get lambda 4, that cancels with this. So how many N cube, lambda cube terms are what? Here 1. 6 minus 2, that's a 4, right? So you have 4 lambda cubed over N, because divided by N4. So I took care of this, took care of this, took care of this. Then lambda squared is 7, minus 6 is 1, plus 1. So 2 lambda squared over N squared. Then, so we took care of this, we took care of this, we took care of this. Then look here, n lambda, 2n lambda minus 2n lambda. So there's nothing else. This is the variance. And the Cramér-Rao bound, if you want, we can compute that too here. So sigma squared CR bound for lambda squared is sigma squared CR for lambda multiplied by d lambda squared over d lambda the whole square, right? So this is 2 lambda. I think we have computed the Cramér-Rao bound for lambda here. So that this is 4 lambda squared. So you see, look at here. This is the variance. I hope you see that variance is larger than the bound. But you don't have to worry about it. This is the best you can do. There is no better estimator because this is already a function of sufficient statistics. So I want you to go home and do a baby example. So why don't you do this example? So if you do the calculations, you'll get familiar and you'll get good at it. So I showed you, so do these 2 problems. What is the best estimator? So I want the best estimator and its variance. Remember, I'm going to call it theta 3, and for theta 4 also. A best unbiased estimator, so of course. And lambda cubed, right? Poisson case, right? Parameter is lambda, not mu. I mean, mu is fine, but we have been using. So this very same problem, but the unknown is lambda cubed and lambda 4. So remember, it will take you some time, and you just have to use, extend these tables, etc. Right? So you may have to go up to 8th order and collect all the terms. So you can see how terms increase and so on. But you will be able to show that the variance is going to be that's the unique feature, the Cramér-Rao bound plus some quantity. So you can clearly see it's not an efficient estimator. So in those cases, the Cramér-Rao bound is a loose bound. Okay, so let me take this problem. That is, you can't do these simple tricks here. So let's say theta is e raised to minus, we need the best unbiased estimator with the minimum most variance. So remember, the key is to use the theorem. Because for a problem like this, we need an unbiased estimator. It doesn't matter how sloppy it is because we know how to clean it up or how to make it efficient or how to make it better, right? So anybody has any ideas? So remember, the random variables are x1, x2, etc., xn. Probability of any one of them equal to k is e raised to minus lambda, lambda to the power k. So I'm writing all this because I want you to see how people think. And so from here, obviously you need to come up with, this is all you have. And these are the observations. So this is not that straightforward, but once I write down the answer, you will see why it makes sense. So you have to make use of this. See, you are interested in e raised to minus lambda, but I also see e raised to minus lambda here. But then I have all this garbage. So anybody? So remember, estimator has to be based on the data, not based on that. But this, together with this, should give you this following clue. So suppose I define an estimate. Remember, I'm trying to estimate this quantity. And as I said, because you have an estimator for this is not even good for it's a square of that. We saw that here. Right? So saying that we'll take the e raised to minus of this is not going to be the solution. It's not going to be unbiased. So suppose I do this. Why did I do all this? Look at the expected value of y now. How do you, y only has two discrete values, 1 or 0. So by definition, it is 1 multiplied by probability of y equal to 1 plus 0 multiplied by probability of y equal to 0. So that's simply probability of y equal to 1, which is the same as probability of x1 equal to 0. What is the probability of x1 equal to 0? Anybody? All right, so you can see, so now you could see this is a clever idea, whoever came up with. That's the reason I put this up for you too. But from here you can see, if you put k equal to 0, this goes away. But this is a laughably sloppy estimator. But that's where the theorem helps. So this is what we are looking for. We have found the estimator. This is, so if you just have to do this last step, that's all. So which I'm going to do there. So the best estimator is so T is, remember, T is sigma xi is Poisson with parameter n lambda. So probability of T equal to K is e to the power minus n lambda, n lambda to the power T over T factor. What is it? T is a sufficient statistics for lambda, but so if you take this parameter, it will be this is two ways you can argue. This is just a function of lambda. So sufficient statistics will be the same. Otherwise, you can call this to be theta. This will be log of theta. So you can see where the joint density function, the data is only going to come sigma xi. So so if you call this to be theta, this will be log theta, right? Minus log theta. Minus log theta to the power xi. So the data comes only there. So that's a sufficient statistics for. So T is still sufficient for e to the power minus lambda. So let's do the conditional density function of. So the best estimator is the conditional mean of y given tx. But look at here, y only takes one value, so that's y equal to 1 given tx equal to. So this is where probability helps. This is why I put the probability as prerequisite. Remember, multiplied by 0, multiplied by something, it's not there. So y equal to 1 is the same as x1 equal to 0, because look at here, y is 1 when x1 is 0. Conditioned on tx equal to t. So that's the same as probability of x1 equal to 0, tx equal to t divided by probability of tx equal to t. Now, how do you find the probability of, I think we did this earlier. So probability of t equal to t. So remember, t is max of x1, x2, etc., xn equal to t. Anyway, for any random variable z equal to t, so if z takes discrete values, then this is true, right? If z takes discrete values, after t, it has to jump to t minus 1. So t less than or equal to t is t equal to t, mutually exclusive union with z less than or equal to t minus 1. Yes? What? What did you say? Oh, yeah. I don't know, I was mixing up problems, right? Yeah, so we don't even have to, I don't know why I started. But so let's do it here, you're right. So this is going to be probability of, this is even easier. All right, so somebody is paying attention. I was mixing up with the uniform problem or something. Look here, how do you simplify the numerator? x1 is 0. Here it says x1 through xn equal to t. So how can we rewrite this as? If x1 is 0, this is the same as 2 to n, right? You can write another line, so I'm just going to change it to 2. I hope nobody has any issues. Because this is x1 is 0, I can write this from 2 to n. But now look at what happened. x1, x2, xn are independent random variables. So what happens to this and this? Anybody? This and this are independent. So the numerator, I can write this as now probability of x1 equal to 0 multiplied by probability of sigma xi I equal to 2 through n equal to t divided by probability of xi equal to t I from 1 through n. So what is the density function of these random variables? Anyone? 2 through n? Poisson with n minus 1 parameter. So let me write down the probability. So the first one is e raised to minus lambda because x1 is Poisson with parameter lambda. Second one is parameter with n minus 1 lambda multiplied by n minus 1 lambda to the power t over t factorial. And the whole denominator is e raised to minus n lambda, then n lambda to the power t over t factorial. So if you do the simplifications, what do you get? Anybody? So this is the best estimator. How can you guess this to be the best estimator? So you need the theorem. That's what I'm trying to say. So this estimator is the one with the minimum most variance for the e raised to minus lambda. So if you want to, so we know that expected, so let me call this to be T naught. We don't have to try this, we know expected value of T naught is e raised to minus lambda. So question is, what is its variance? So first of all, what is sigma squared CR? So that's going to be sigma squared CR for lambda multiplied by the derivative of the parameter squared. So this will come out to be e raised to minus 2 lambda. What was it before? Is it lambda over n or sigma squared? Anybody?
Change the t to the sufficient statistic itself, like the lowercase t to whatever we had before.
Sigma xi. Right, so this will be sigma xi. And this is right. Was it lambda over n? Right. So this is the Kramerov bound. So I'm going to find the variance for T naught. Right. So that's going to be square of the expected value of the square minus the mean squared. Mean is e raised to minus lambda, right? So I'll do as much as I can, then I'm going to leave it to you too. So let's do this term. That's the harder term, expected value of T naught squared. So that's going to be T naught is what? T naught is n minus 1 over n to the power k, probability of t equal to k. Right? Yes? So this is going to be summation. Oh, we have to square this. So this quantity, no? This quantity, so this will be 2k here. So this is n minus 1 over n. And parameter is e raised to minus n lambda to the power k over k factorial. So e raised to minus n lambda goes outside. Then I hope you see that this you can write it as right. This is n minus 1 squared, n cancels. So n minus 1 squared to the power k, n to the n squared and n to the power k. So n is here, lambda k is here. So this is e raised to minus n lambda. Then you have e to the power this quantity. So e to the power this quantity. That I'm going to expand. That will be n squared minus 2n plus 1 over n. Multiplied by lambda. So you can see n lambda will cancel, so you get e to the power minus 2n e raised to minus 2 lambda multiplied by e raised to lambda over n, is it? And if you expand this e raised to minus 2 lambda, this will be 1 plus lambda over n plus lambda square over 2n squared plus etc. But look at here. Did I miss something?
E2 minus 2 lambda cancels with the minus.
Oh, yeah, we haven't even, this is only square, so this, when you take this off, that's what I wanted to say. The variance, so let me write down the variance here. So the variance expression will turn out to be e raised to minus 2 lambda over lambda over n. Then you have 1 plus lambda over 2n plus etc. So what's the moral of the story? Look at here. The Rao bound term is the first term. Then you have some extra junk. So this is not an efficient estimator, but this is the best you can do. So here we have used, this is a non-trivial example. We use the Raw Blackwell theorem to come up with the best unbiased estimator.